Okay, finally. Good afternoon, everyone. It is an absolute pleasure to introduce a distinguished figure whose groundbreaking contributions have left an indelible mark on the fields of architecture, computational design, and advanced construction technologies. Professor José Pinto Duarte exemplifies the perfect synergy between academic excellence, innovative research, and practical applications, making him a true pioneer in shaping the future of architecture and sustainable construction. José Pinto Duarte is an acclaimed architect, researcher, and academic leader with a distinguished career spanning architecture and computational design. He earned his professional degree in architecture from TU Lisbon and pursued advanced studies at MIT, where he completed the master's and PhD in design and computation. Currently, he holds the prestigious Stuckman Chair in Design Innovation and directs the Stuckman Center for Design Computing at Penn State. In addition, he is a professor of architecture and an affiliate professor of architectural engineering in the same institution. Previously, José Pinto Duarte served as Dean of the Lisbon School of Architecture and co-founded Penn State's Additive Construction Laboratory, ADCAM Lab, and XAB 3D, a groundbreaking company in mobile 3D printing for construction. His research focuses on the intersection of computational design and advanced construction technologies in phasing, sustainable housing, and mass customization. José Pinto Duarte's innovative work includes designing 3D printed habitats for extreme environments and achievement global recognition through projects like NASA's 3D printed Mars Habitat Challenge, where his team won second place. José Pinto Duarte's Keynote, Additive Construction on Earth and Beyond, from research to practical applications, explores how advanced 3D printing technologies developed at Penn State's Additive Construction Laboratory address the global housing crisis, highlighting innovations in sustainable materials, mobile printing systems, and design optimization tools. The presentation showcases projects like 3D printed homes in Alaska and Mars, habitat prototypes. By integrating these cutting-edge solutions, José Pinto Duarte demonstrates how research for extreme environments can transform construction practices on Earth, enabling efficient, sustainable housing worldwide. It is with great respect and appreciation that the organizing committee of the 7th International Symposium of Formal Methods in Architecture invites Professor José Pinto Duarte to share his invaluable insights with us. Thank you.
Hi, can you see my screen? Can you see my screen?
Yes, we can see your screen and now we can hear you. I'm sorry, just now.
Okay, very good. So good morning, everyone. Thank you so much for
just
this
a
invitation.
moment. Just a moment. There's something with your screen. Maybe you could make it full screen. We can see.
Okay, so let me do the following. Just give me one.
Yeah, we were seeing your presentation notes and not
And now?
It's the same.
Okay, so let me see. I have an idea. Just give me 1 second. And now?
Yeah, perfect. Thank you.
Okay, very good. So, sorry, just 1 second. Okay, so as I was saying, good morning, everyone. Thank you for this very kind invitation. I regret that I'm not able to be there in person, but I'll do my best to share with you the research that we have ongoing on concrete printing at the ADCON Lab and at XAB 3D. So I've entitled this presentation Ongoing Research Roadmap at the ADCON Lab and XAB 3D, just basically describing the kind of research that we are developing at the moment. As the introduction, sorry, I'm having problems with the presentation. The slides are not moving. Okay. So the ADCON Lab is a multidisciplinary group of people with varied backgrounds in terms of knowledge, expertise, but also ethnic and cultural background, which gives us a good environment to develop research. Because anytime we need to address a problem, people come in with different ideas based on their expertise and background. So this slide show the facility. Actually, we have just moved the lab again, so the slides are not up to date. We moved the lab again because we continue expanding, but you can see the printing area, the control area, and the cleaning area as well. So the mission goals of the lab is to support the integration of digital technologies in design and construction, contribute for the achievement of the United Nations Sustainable Development Goals. But I should say that the focus is not on technology, but on strategically deploying technology to address contemporary social issues. So this is a graph that I always like to show in my presentations at the beginning because it provides the motivation for our research. So the graph shows the growth of human population. It's basically telling us that over the next 20 years, we will need to build as many houses as we've built in the previous 2,000 years. So again, in 20 years, do as much as we have done in the past 2,000 years. So what's the solution? So the solution that we have been advocating is to use digital design and production systems, meaning systems that are controlled by computer systems. Basically, the design system reads information about the context and outputs a solution, and the production system uses that solution to actually materialize it. So the basic idea is to have rule-based design systems that will even allow lay people to design their own houses. And this works not just at the housing level, but also at the urban level. And then we use artificial intelligence to optimize the design for specific requirements, like minimizing energy consumption or maximizing the capture of sunlight and so on. So once we have found a way to customize the designs, we need a way to very expedite mode materialize those designs. So there are several possibilities. The one that we've been focusing on lately is the use of digital 3D fabrication. That's what you see on this slide. So basically, you see the printing of the capital over a very large column being printed at the ADCON lab. So that's the basic idea. So rule-based design to customize the houses, digital fabrication, digital 3D printing to make the houses. So the goal of the lab is to develop a mathematical model of the process of 3D printing. So basically, 3D printing is a very complex process with many different variables, like environmental variables, like the temperature and humidity, the material composition of the mixture that's going to be extruded, the type of binder, the type of aggregates, the admixtures, use of fibers, and so on. And then this has an impact on the material properties, like flowability, printability, the setting time, density, strength, and so on. And then you have variables connected to the printing system, like the dry feed rate, the water flow rate, the pump speed, the speed of the robotic arm, the length and diameter of the hose, and so on. And then we have design variables like the filament shape in terms of height and width, the number of filaments and the number of layers, and the specific tool paths used to print, extrude the material. And then you have variables associated with the building itself, like the shape, size, textures, colors, and so on. So again, what we are trying to do is to create a mathematical model relating all these variables so they have a complete control of the process. So let's talk about each of these elements at a time. So about materials. So our goal is to develop sustainable extrudable mixtures. As you know, Portland cement is not a very sustainable material because it consumes a lot of energy to be produced, and has very big CO2 emissions. So we are trying to develop new types of concrete that do not consume the energy consumed by Portland cement and have less carbon emissions as well. So we are looking at magnesium oxide, magnesium sulfate, citric acid, and so on as the main trigger of the binder. And then we are developing also lightweight mixtures like that you can obtain, for instance, by replacing river sand in the concrete mixtures with lightweight materials like cork granules or expanded clay or a styrofoam and so on. So the idea is to develop mixtures that are lighter and therefore have a better performance in terms of thermal insulation, or do not impose such a big weight on the structure. Self-weight will be decreased. So that's an example of the type of material that we are developing. So what we do in this case, so we basically try to understand the material, the properties. For instance, in this case, we replace the river sand by cork in different amounts, like 25, 50, 75, and 100%, and see what are the properties that we obtain with the materials. For instance, is the material still pumpable? Does it flow? What's the open time? And then we also look into things like, what's the mechanical performance of the mixture for different amounts of cork, and see, if we can be within the range required by current building codes. So that's what these graphs are trying to show. In this case, also in terms of permeability and thermal insulation. As you can see, as we increase the amount of cork, the conductivity of the material decreases, so it gets a better performance in terms of thermal insulation. So basically, you have to deal with all these aspects: strength on one side, thermal insulation on the other, pumpability as well, and so on. So this requires extensive testing to find out, what are the ranges of replacement of cork that allow you to have a mixture that works, that it's flowable and has the right strength. Another example is the expanded polystyrene. This is another type of concrete that we are trying to explore and develop. So basically, these materials decrease density, increase insulation properties of printable concrete, but it also transforms the mechanical properties to ductile, allowing it to withstand considerable deflection. So not just thermal insulation, but also improvements in terms of deflection. This is the work of one of my PhD students a few years ago. So basically, in this case, what we are doing, so we are changing the proportion of cork in real time so that you can fully customize and optimize the design of building components. For instance, in this case, it's a wall with a door. And what we do, we use finite element analysis to understand how the loads are distributed along the wall. And then we are going to make a material that is stronger, place a material that is strong on those parts of the wall where the loads are stronger, are heavier, and do the opposite when the loads are lighter, so we can increase the amount of cork. So we are optimizing the building element, the wall in this case, for structural performance and thermal performance at the same time. So you end up with building components that are high performance in terms of thermal insulation and structural strength as well. So the element that you see on the right-hand side is a wall that has a higher amount of cork on the external part of the wall. And how can we accomplish this? So you basically have two pumps, one with concrete with river sand and the other one with concrete with cork granules. And by changing the relative speed of each pump, you can increase or decrease the gradient of cork. And therefore, when you deposit the material in space, you deposit the material with the properties that you want, and basically fully customizing the design of the building element. So now about the printing system. So we started very small with a very portable robotic arm and a very portable printers in a very small room. And as time went by, we continue increasing, the quality of the printing system and the performance. So we increase the size. So we had to move the lab several times as we were developing the system. And you see at the bottom on the right-hand side, the system that we now have at the lab. So basically a system to print with concrete needs a computer, a robot that controls, a control that controls the robot, and the robot itself, the mixer basically mixes the dry mix with water, and then the pump to extrude the fresh material through a hose that ends up at the nozzle that is controlled by the robotic arm, and then the robotic arm moves according to the instructions set by the code to print the parts on a platform. So this is actually, we continue developing the system, and we created a company, which is Accept 3D, to basically sell the printing system that we developed at the lab. So the Accept 3D has different types of printing systems. One that we really particularly like is a mobile printer that runs on tracks, and it's ruggedized, so it can actually go out on the terrain and very difficult terrains to print, as you can see in these images. It also has a lift that allows you to go up and therefore print buildings with 2 stories, as I will show in a few slides. So basically that's the work at Accept 3D, and I will show more of this work. So now, so we are talking about the whole system, the entire system, but there are also details of the system that can be improved and developed in a more sophisticated way. Like in this case, so we are developing a nozzle that we call the smart nozzle that has several capabilities. One capability is that it rotates in a way that allows you to remain perpendicular to the tool path. So as you curve, the nozzle rotates so that they're always in the same position relatively to the printed filament. So these are several advantages. One of them is to increase the strength of the material, but also allows you to design shapes that are more complex, and also allows you to control the direction of fibers in the concrete filaments. As you can see in this case, then you can use different types of nozzles. If you have the rotation nozzle, you can use different types of endings to extrude the material with different shapes. And you can see in this case that if you use a trowel to smooth the surface so you don't see the lines, or actually the lines became a little bit more faded as you print, it increases the strength of the wall of the building component. And then the other capability is to add the admixture. So there are different types of admixtures. One is can be an accelerant. So the accelerant, what it does, it reduces the time for the material to get hard. So, and if you do that immediately before extrusion, the material retains good flowability properties while it's going through the hose. And then once it's extruded, it will harden very fast. Obviously, the research that we develop in this case is to define what's the right amount of admixture to be injected before extrusion. If it's too much, it will, set too fast and clog the machine, or you get, as you can see in these images on the right-hand side, not a very good printing quality. So in this case, for this type of mixture and for the type of admixture that we were using, 2% was the ideal amount of admixture to add to the nozzle. And then another aspect is a closed feedback loop. So what happens? when you are printing, we need at least 3 people. One is controlling the robot, one is controlling the extruder, and another one is overseeing the operations. So you need to keep an eye how the things are going, like if the material becomes too wet or if it becomes too dry. So you need to adjust, the settings in real time. For instance, you need to increase or decrease the amount of water, or you need to increase or decrease the pump speed or the robotic arm speed. So what we are trying to do is to automate this process, finding a way to monitor the printing process that requires less people. So we are looking at vision-based monitoring of the concrete printing operations. So basically, we have a camera that's attached to the robotic arm and follows, the printing process, and is able to detect variations in the shape of the filament and immediately, trigger procedures if something goes wrong. There are different ways of using systems like these. One is, before you start printing, like for instance, you want to print on a site that's not leveled, or that is not regular. So we use this system to create a 3D model of the site. It will scan the site, and it will adjust the toolpath to the irregularities of the terrain to make sure that the nozzle, for instance, does not get buried on the ground. So this is, a use of the system before start printing. And then you can use the system during printing to monitor the quality of printing, the shape of the filament, the shape of the layer, the shape of the entire part, to see if it's deforming, and if it's deforming, what might be the cause. It lead to structural failure if you don't act. So, and therefore, if you follow the process this way, you can change the printing settings to remain within the acceptable and the right, so that the variables remain with the right values. And then you can also use, after you print, just to compare the shape of the printed parts with the shape of the design and see if there were any deviations, and if, to guarantee that we achieve good printing quality. So that's basically, the idea. This is the work of another PhD student to detect, predict, and prevent geometrical defects in concrete printing, and how to adjust the toolpaths and the printing settings in real time to prevent that from happening. So you can see some images of the machine and the process being used. So we are basically using shape grammar rules to decode what the machine sees, what the camera sees, and define and trigger the right action, which might be, as I mentioned before, the content of water, or the speed of the pump, or the speed of the robotic arm, or even, a change in the toolpath. So basically, we have 3 steps: scan, interpret what the camera sees, and then act to correct what's not going well. And this is how you can use the system for, in a more elaborate way, data acquisition, data processing, defect detection, defect classification, diagnosis, meaning finding out what might be causing the problem, and then, decide which action to take to counteract what's going on. So basically, with this way, we can control a very good control of the shape of the printing filament, and you can design adjust the toolpath in real time to changes, the detected changes during the printing process. So another area of work is reinforcement. As you know, concrete has a very good compressive strength behavior, but not very good in terms of flexural strength. So it's important to use reinforcements like, steel or RFP, rebars, and other types of meshes to increase the flexural strength of the printing part. So what we do, we conduct several types of tests to find out what's the compressive and the flexural strength of the mixtures that we are producing. and then you need to find out which type of reinforcement needs to be used. So basically, the goal of this of the research in this area is to investigate different methods of reinforcement. And again, like the scanning, you can place the reinforcements before you start printing, or you can place the reinforcements during the printing process, or you can place the reinforcements after you print. Like you see in this slide, you basically inserted rebars in the 3D printing structure, and then you're going to pour concrete to finalize the structure. So there are different possibilities for the reinforcement. So what we do, we conduct several tests to understand how we improve structural performance of the 3D printed concrete with different types of reinforcement. So we conduct, compressive strength tests and flexural strength tests as well. So in this case, these are walls. So as I will explain later, we are designing a house to be built in Alaska. Alaska is a very harsh environment with lots of earthquakes, very strong winds, and the very differences in temperature. So we need to make sure that the 3D printed concrete has the right properties and can endure such conditions. So we printed wall segments, and then we tested the wall segments for flexural strength to make sure that they could withstand earthquakes and the strong winds that blow sometimes. So ultimately, what we want to develop tools for designers that need to design 3D printing structures so that they can predict the structural behavior of parts with different types of reinforcement. So basically extending finite element analysis to 3D printed concrete with reinforcement, so that you have a design tool for you to use in the design of these structures. So this is an example. So these previous examples were about inserting the reinforcement after printing. This is work that we are doing within printing processes. So basically, what you do, you introduce the reinforcement as you print. In this case, the goal is to print horizontal slabs. So the idea is to print the filaments with cables inside. So you basically unwind a cable, and then you print on the top of the cable. So you end up with a reinforced filament, and therefore you can print slabs without any kind of formwork, which is a goal, so that you can take advantages of 3D printing technology. So that's the basic idea. And then, because this is the process, you don't need to print a flat surface. You can also print a ruled surface like you see in this case. And then you can do this in several layers, so to produce slabs or surfaces with different types of strength, with levels of strength. So this is basically, so we also have a smart nozzle in this case that unwinds the cables and then prints the concrete filament on top of these cables. And then we conducted tests to see what's the strength that you can achieve with this process to make sure that we are within the acceptable or the strength required by the building codes. So this is a video, I think, as you can see. So you see the nozzle on this side, and you're going to see the filament being printed. So as you can see, the cables are being placed, and the filament is printed on top. And you can see on the right-hand side, then you can span. You don't need to print the filament side by side, but you can bridge filaments that are 8 centimeters apart, and therefore you can make the structure lighter as well. And then for design of additive construction, it's important to have tools. So I'm going to talk about a platform that we developed for the NASA competition. So the NASA competition required us to design habitats for Mars, but then we had to test the habitats on Earth. So we actually had to print, an instance of the habitat on Earth. So Mars and Earth are two very different environments. As you know, Mars has lower gravity because it's a smaller planet. And because of that, it also, its ability to retain atmosphere is lower. So the atmosphere on Mars is about 1% of the atmosphere on Earth. And then you also have, cosmic radiation So it's basically, it's an extreme case of a very harsh environment. So instead of developing two different habitats, we developed a platform. So it's basically a beam-based platform with four capabilities. So one is a generative system. It's a rule-based parametric design system that allows you to generate different configurations. So you define the rules, and then you can, create a universe, a potential universe of design solutions. And then what you do, you have the second component is does performance analysis for structural performance or thermal performance. And so you're able to rate and rank the different possible configurations of the habitat design. And then you use optimization to find what's the best configuration. So basically taking into account, gravity, atmospheric pressure, cosmic radiation, and so on. And then once you are able to find a design that works and that is optimized, then you use the force module, which is a construction simulator that simulates the printing process and is able to detect if the two robots, in this case, because we were using two robots, one to print, another one to place, in this case, the window frames. So make sure that the robots will not collide during the process because they were working simultaneously. So that's what the construction simulation does. So this is the output of the system. You see on the left-hand side the design for Mars, and the right-hand side the design for Earth that we actually printed. So this is a video. So this is the construction simulation. So that's basically a video that we developed to and qualified us for the finals of the competition. Basically, we had a limited type area of space to set up. So we needed to show that we could set up our system within the available area and then show how it would print. So you see there's a big silo, there's a tank of water, and then they both feed to a small silo and a pumping machine that's connected to the robotic arm, and the robotic arm is going to print, while the other one is going to place the window frames. So that's basically what you see in this case. It's starting to print, and then it's going to place the window frames at some point, as you can see in a few moments. So what happened while we were printing, we changed the toolpath design in the last minute. And because as you can see there are two windows that are very close to each other with a very small pillar in between. So because at the time we do not have the capabilities that we have today, the pillar deformed, and when we had to insert the window frames, they didn't fit because the space was small, so we actually had to use a hammer to put them in place, and that informed the continuation of research, as I will explain later. So this is an image of us at the competition. As you can see, the setup is very close to the video, and we're printing the very large structure. And then you see the robotic arm to place the window frame, and the other one to print. So once we have this platform, we can continue developing tools to support the design of structures. So one idea that we have is to print not just the walls like everyone else is doing, but print everything. We want to print the foundation, we want to print the walls, we want to print the horizontal slabs, and you want to print the roof. So we are looking into vaults and domes as a precedent to use in the printing of roof structures, and trying to understand how they can be printed, and then develop the tools to verify the performance of the structure. So in this case, so basically what we're doing is assess structural performance of the concrete in the fresh state while we are printing. So there are tools on the market that can be used to assess the performance of structures once they are in place and they are hardened. This has been used for cast concrete, but you also need to verify how does the structure behave while it's being printed when the concrete is still in the fresh state. So that means different levels, different layers have material with different properties. because, for instance, in this case, if you start printing from the bottom layers harden, and then when you go to the top, the bottom layers are hard, but the other ones are in the intermediate stages of hardness. So, and you need to understand, if the structure is strong enough to avoid collapse during printing. So, one thing we need to do is to have an element of the system to predict the shape of the filament. So they know exactly, for instance, you need to make sure the filaments have a good bonding, both in terms of vertical bonding and horizontal bonding as well. So you need a filament predictor to understand the shape of the filament. And then you need to simulate the structural performance of the material, taking into account that different layers are different stages of hardness, and therefore have a different level of strength. And then you can do the simulation, the finite element analysis, taking into account these differences in the material properties. And then you develop the tool path generator. So you basically, what you do, you generate the overall shape of the parts, you develop the tool path, you do structural simulation during the printing, and then use optimization to find out what's the best tool path design. And best in this case means, avoid collapse, and at the same time decrease the use of material, and therefore decrease the time of printing. And then, so as you could see, in this case, the vault is still uses a lot of material, and it's still very steep. So we are trying to find ways to decrease the angle so we can print vaults that are shallower. And that's exactly what we're doing. So basically, we are looking into different slicing strategies. So the traditional slicing process is horizontal. You basically slice the part horizontally to reconstitute the part during the printing, but you can also have different printing strategies. You can, using, slicing strategies that are not necessarily horizontal. For instance, in the case of vaults, you can use radial slicing, or you can use inclined slicing. In radial slicing, it's very complicated because it means that you need to have a layer with varying height. So let's see how this can be achieved. So in this case, we are just using horizontal and diagonal slicing, and trying to understand how to move from one to the other and see if the part is printable. You can see, the parts. It looks at it collapse, but it did not collapse. It's being printing this way. There's a lot of over extrusion on the bottom part, but this was a successful test in this case. So we are extending the BIM platform to do the structural analysis of vaults and domes, and with varying slicing strategies and different design strategies as well. So with the idea of printing the entire structure, the foundation, walls, and roof. As you can see, you can use different types of design strategies to increase the strength of the part and make sure that it will not collapse, because the idea is to print the vaults and domes without any kind of support. So the other one is to understand the material behavior. For instance, I mentioned before that when we were printing for the NASA competition, there were two windows that were very close to each other as a small pillar in between, and we changed the tool path. So there are basically two possible strategies. One, you would go around, stop printing, bridge the opening, print the pillar, continue, bridge the opening, the other opening, and continue printing. So we change the tool path in the last minute, so we would print the walls around the windows, and then we'd print the pillar at the end. The problem was the pillar was too small, so when it was printed, it allows lots of deformation. And because of that deformation, we were not able to insert the window frames automatically. So this trigger work to understand how the material deforms. So basically, if you need to print a cylinder in a small part, if you don't do any kind of compensation for the deformation, what's going to happen? You end up with a truncated cone. So the bottom layers will deform under the weight of the subsequent layers. So you need to change that. So you need to develop an algorithm that counteracts the effect of the deformation. So basically, if you want to print a cylinder, you actually use the algorithm to deform the design shape so that you have an inverted truncated cone. So when it gets printed, it's going to deform and get the right shape. So that's exactly what this slide is showing. On the right-hand side, you see a cylinder without any kind of compensation. So it actually will lead to collapse, to plastic collapse. And then you see different types of compensation strategy, different types of algorithms. You can see the successful one is on the right-hand side. In this case, we compensated for both, horizontal deformation in terms of width, but also vertical deformation. So what happens if when you print and the bottom layers deform, they will increase their width, and then they will become shorter as well. So the distance between the nozzle and the previous layer will increase over time. So you need to compensate for both, deformation in terms of width and in terms of height as well, so you can get the right shape. So now we are developing a more sophisticated type of filament predictor. So basically using machine learning to understand what are the combination of printing settings that lead to filaments with certain properties. So basically, this is the idea. So these are different variables: the diameter of the nozzle, the height of the filament, the distance between the nozzle and the printing bed, and the speed of the robotic arm. And you need to understand how these variables, so they basically are impacted by the printing settings, like, robotic arm speed, the pumping speed, extrusion rate, and so on. So what we did, we conducted several experiments. As you can see, we printed a filament. Each segment of this filament has different printing settings. So you were changing the settings in real time. And then you can see some worked really well, have a very good shape quality, where others have a terrible shape quality, and some eventually collapse. So this was studied. So we classified the resulting filaments into different categories. And then we use machine learning to understand the correlation between the printing settings and the quality of the printed filament to find out, basically what printing settings lead to good filaments. And then we can use this system to adjust the printing settings before printing, or actually in real time as well. So this allows us to print filaments with varying width, like you see in this case, but also with varying height. So in this case, you see a structure that we use radial slicing, and so the layer has a varying height, and we use this algorithm to control the printing process to get the layers with that type of shape. So additional research threats. So basically, for instance, for environments like the moon or Mars or even Alaska, you need to develop a completely sealed structure. For instance, in the case of Alaska, air leaks are terrible because they lead to huge energy consumption. Because, in Alaska, you can get to -50 Celsius degrees. So you need a completely sealed structure to make sure, that you don't lose any energy. And then you have to do durability tests. So basically, in the case of Alaska, we are working with the University of Alaska in Fairbanks. So we printed concrete parts, and we put them in environments, artificial environments that simulate the freeze and thaw cycles that you exist in nature. So basically, you go to a certain temperature, then you raise the temperature and go back down again, and so on, to see if the printed concrete is durable enough to withstand the rigors of the climate. And then you are also developing research to automatically place, the technical installations in window frames or reinforcement, and so on. So as you can see in this case, a window frame is being placed. These were tests that we did before the NASA competition preparation for the finals. And then so you can also, use the same system to place reinforcement, as you can see in the bottom image. So you'll see the frame will be put in place. This is exactly what did not result at the competition because of the explanation I mentioned before. The pillar deformed too much. So we didn't have the algorithm to compensate for that before. And because we are also concerned with aesthetics, we try to understand the type of textures and complex shapes that can be created without formwork. So you see examples of work by students in my concrete printing class. You can see, the work each year. The studio has a different theme. This year was the design of 3D printed tiny houses. In the years before was the design of structures to support, trails. So every year the topic changes. So you can see in this case the printing of a cylinder with a very good printing quality, thanks to the use of all those algorithms to control the printing process. You'll see also different strategies to transition between layers, so you can actually use it to your advantage to create a certain aesthetic effects and so on. So you will see in this case the cylinder being printed. In this case, you're going to see an inclined wall being printed. You're going to see that at the end, a little portion of the wall is going to collapse, and I will explain why. Let's see the collapse first. So what happened in this case is in the design of the toolpath, they designed the toolpath in a way that, when you transition between layers, you went back on the layer that had just been printed. So it did not have enough time to harden. So when you print the next layer up, it's going to deform too much. And that's what led to collapse in this case. So you need to take that into account into design of the toolpath. And that's why you need the simulator and the toolpath optimizer to make sure that you avoid situations like this. So I'm going to show some projects that are being developed at Accept 3D. So again, Accept 3D is a company that was created as an offspring of the AdCon lab. So it's a startup company. So this is a work that the goal is to design and print artificial coral reefs to protect the shore. So you can see, the complex shapes that needs to be printed, and that's exactly what we are doing. And also, we are using different materials. We are using the functionally graded materials idea. So we have concrete, for instance, in these bottom parts. The core is actually a different type of concrete than the outer layer. So the outer, in this case, is a very strong concrete to guarantee structural stability, but the core is actually a different type of concrete with uses hemp to do carbon sequestration. So the idea is to contribute to avoid the climate change. This is another work that's being developed. This is actually using microwave technology to sinter concrete on the moon. So in this case, avoid the use of water and use microwaves to sinter the concrete. So some examples of the work, you can see the printer on the left-hand side, with the robot raise using the lift, and if some of the complex shapes that we're printing for clients. And that's part of the research that we're developing. So this is actually very recent. This image on the right-hand side was from last night. So we're printing a column that has about 24 feet. It's 24 feet tall, so 10 feet is 3 meters 6. It's about 7.5 meters tall, so it's higher than 2 stories. So this is the section of the walls. This is a printing test that we run in the lab before going out and print the column. So the column is not finished yet. So today we're gonna print the last bit of the column. So as you can see how high you can print with this printing machine. So going back to the beginning, the housing projects. So we have several ongoing projects for housing. This one is for Alaska. So basically what we did, we analyzed traditional Alaskan, I mean, by traditional, I don't mean the igloos. I mean, you know, which type of houses are currently used in Alaska. Did a study of them to develop a shape grammar. So basically different types of functional organizations. You see in this case, there's a divide between the private and the common areas of the house. So the private areas are indicated by the red and the common areas by the green and blue, while you know, the yellow is a circulation. So the idea is to be able to develop different types of housing with different number of bedrooms and different details as well. So this is a different arrangement. We have the living, the common areas on one side, on the other side of the circulation. So the division between circulation, between private and common areas is defined by the circulation, as you can see at the bottom. So this is, you know, the one that actually we are exploring. Basically, you have the service area on one side of the corridor. So this has several advantages. So the idea is not to use the walls to run any kind of pipes. So you keep the pipes on the floor. So by using the strategy, you know, you're basically creating a wet area on that side of the house. And you see, you know, the house with different number of bedrooms. Because if it's Alaska, we need to have what they call an Arctic entry. So it's a transition space between the outside and the inside, so that when you open the door, there's not a loss of energy. Remember, it can be at minus 50 Celsius degrees outside. And then studying different strategies to place the house on the lot. So you basically, this is the lot size of the prototype house that you're going to build. And basically the lot can have two houses. And this is actually, you know, a study on how the houses could be laid down on site. And then, but the idea is not just to print the house, but to print housing complexes. So you see in this case, all the houses are different. And then in this case, 4 different blocks with all the houses, different strategies. For in some cases, you have the service area overlooking the courtyard. In the other case, it's the opposite, and so on. So this is the house that's going to be printed this summer. So basically, it's a 3-bedroom house. So basically, it's one of many possibilities. That's the one that the town hall chose to print. And you see the construction details of the house. So you basically, because it's the first house, it's a prototype house, we are not taking too many risks. We are just going to print the walls in this case. The foundation, it's a slab on grade, a cast slab on grade. It needs to be completely insulated. So even when you design the wall, you need to design in a way that you completely avoid any kind of thermal breach, which was a very big challenge in this case, but I'll show you how we overcame the problem. So this is basically a mock-up of the house that we printed in Fairbanks in last July. So we printed this small structure to test the building solutions for the house that we print next summer. And we have installed sensors in the house and to see how it behaves throughout the winter. If we are able to keep the temperature at the right levels inside without the loss of too much energy or too much energy consumption. So as you can see, the wall has a structural pane, as you can see on that side, and then is a cavity between, you know, the finishing veneer, which is here, and then we're going to inject foam. Actually, you see the foam after being injected in this case. So it's a closed cell sprayed foam, and there is a complete separation between the inside and the outside of the structure. So in conclusion, we have the technological means to provide everyone with a decent home. The technology used to colonize outer planets can help solve housing shortage on Earth. So it does make sense to do this kind of investment, you know, study how to build houses on the moon or on Mars, because the technology can be used with many advantages on Earth as well. So the opportunities for the additive manufacturing of construction are tremendous. very big opportunities. The use of BIM-based design platforms informed by artificial intelligence can optimize the process and the product and transform the construction industry. So basically, through the use of BIM and artificial intelligence, you can design buildings that have a very high performance. So this slide tries to show some of the advantages. So, linking features of the process with advantages like, high user satisfaction, increased safety. You increase safety by decreasing the amount of people on site because everything, there's a high degree of automation. But you can also lower the construction time because it's much faster to build houses in this way than using traditional means. And therefore, you can also lower the construction costs. And because you can design buildings that have high performance, you have a lower operation cost, so you consume less energy. But you also have a lower maintenance cost because you are avoiding, things like, interface between different materials as much as possible. And as you know, these interfaces are actually a source of building pathologies. And there you're avoiding that, so basically you're decreasing the maintenance costs as well. And because we are using, sustainable forms of concrete, and because we are saving energy and using less material, the lower ecological footprint of architectural housing with this technology is lower. And it also gives you increased design freedom. So you can, build and design shapes that would be very difficult to build and design otherwise, or be very costly. And you can play with the textures. In the future, we can also play with colors as well. And because we are using local sources of materials, we are decreasing CO2 emissions due to transportation of materials, across long distances. So in conclusion, with additive construction, we can build safer and faster houses that are customized, more affordable, high performance, and aesthetically pleasing, with a lower ecological impact. And this concludes my presentation. Thank you very much for your attention. I'm open for questions.
Dear Professor José Duarte, I thank you very much again, because I must say to the audience that Professor Duarte participates in our symposium since the first one, 30 years ago. And thank you also for your beautiful presentation. I would like to the audience what you would like to ask Professor José Duarte. Maybe I make the first question. Of course, I know the work of Professor José Duarte on the former work on the design. He presented something, but I think you made accentuation of the production part of the construction. If you see the Wikipedia page on architecture, you see there that there is at least a popular understanding of architecture as design, and the construction is something that is opposite to design. I'm citing the Wikipedia page. So how do you understand the need for the architect and architecture to participate also in the production phase of the building, of making the building and the built environment?
Thank you for your question, Franklin. And again, thank you very much for this invitation. So if you go back in history and you look at the treatises of architecture like Vitruvius, Palladium, and so on, you see they always have a chapter on construction, because it was impossible to dissociate architecture from construction, because, basically the design is the conception of the building, but the building needs to exist in the real world. So it needs to find ways to be constructed. I don't see any conflict between the two. I see that they need to go hand in hand for a successful project. So the thing with 3D printing technology is that we are merging the two again. So because of increased specialization over time, there was a gradual separation between architecture, between the design aspects or the aesthetic aspects, if you like, and the construction aspects. And then even in that case, there was an increased specialization. So you have, a design team is a very complex team with, different types of architects, different types of engineers, especially for complex buildings. With this technology, you actually need to merge everything back again because you cannot dissociate the design from the construction. I like to cite my former advisor, Bill Mitchell. He used to say, you can only design what you can build. You can only build what you can design. So there's a link between the two. And I think 3D printing technology illustrates this very well. And therefore, I think you need to have a complete understanding of the technology to be able to know what you can design and design in a way that's adequate. I hope I answered your question.
Thank you. Well, for you. Okay.
Hello?
Yes.
Okay. Hello. Thank you so much for your presentation. It's inspiring for us to have a Portuguese man leading the way in these novel fabrication systems and resolution of problems. Regarding the construction of vaults and domes, I would like to ask you if you ever considered doing prefabricated elements like panels, or even if we can talk about classic stereotomy like voussoirs, so that you can overcome the problems of hanging uncured element parts.
Right.
Thank you.
So that's a very good question. So basically, our work has been focused on printing on site, but obviously that's only one way of using the technology. You can also use this technology to print in factory, so to make prefab elements. So you basically have three strategies. One is you print in factory, ship the parts to the site and assemble them on site. The second one, you print on site, but not in place. So then you can, print them on the site and then put them in place. And the third one is actually to print in place. So you are mentioning the possibility of using prefab to avoid some of the limitations of printing in place. I agree. You could actually completely develop, for instance, a panelized building system for housing or for office spaces, office buildings, using a prefab strategies. That's completely possible and completely acceptable. And and you will be able to take some advantage of the technology if you follow that process with other advantages as well.
Thank you.
I don't know. Is this working?
Yes.
Seems that is working. Thank you so much for the delightful presentation and for the groundbreaking work. I'm just a little bit curious about when in your mix of the concrete and the different mixtures of the concrete, where you start using different types of materials, especially because it seems that from the slides that you showed, the EPS, so expanded polystyrene, was the one that was giving more decent mechanical properties and thermal properties as well. But it seems that is at odds with the argumentations of low carbon structures, because on one end we have concrete, which is has a lot of embedded carbon, and also we have an insulation material that has a lot of embedded carbon. So how are you balancing this out?
Good question. So first of all, we are not using Portland cement concrete. We are using concrete that uses fly ash or other types of binders. So basically, the Roman concrete, the concrete that Romans use pozzolanic materials, which is basically a natural fly ash. So we are using forms of concrete that use artificial fly ash as byproducts of other industries. So that's one way to avoid or to address the climate change concern. So using sustainable forms of concrete. The other one is to use, lightweight aggregates that have a better environmental performance as well. I actually prefer the use of cork granules or expanded clay because they are better from the environmental viewpoint. But even if you use styrofoam balls, so basically what you have in this case, so you are making the structure lighter. So in the long term or in the long run, you're actually decreasing the amount of material that you use. You might be using, styrofoam that has not a very good environmental performance, but overall you're actually improving the performance of the building from the environmental viewpoint by using less material and consuming less energy.
Thank you. David?
Hi, David. I
Hi.
was wondering, I'm really interested in this work that you present about Alaska. In where in the process inputs like environmental characteristics of the site is introduced to, in a way, define the sort of mix in the material that you set to do that house in Alaska. For instance, temperature, humidity, wherever. Is that input in the process, or you just know the characteristics and it doesn't, is part of the mixture, if you want, of the materials that you are going to set in order to build the house?
So we take into account local conditions on different levels. So starting with the material. So we are using a concrete that we have developed specifically for Alaska. That means, sorry. So that means basically using indigenous materials. So we are looking what's available in Alaska that can be used to make concrete. So we are using local sources. So that's one way. For instance, we are building a house in Nome. Nome is very close to the polar circle. There are no roads to get there. So you can only get the materials there by using local materials or barge them. So basically use a boat to get the materials or even an airplane. But as you know, an airplane is not very sustainable and it's very expensive as well. So using local materials is to make the concrete is one. The other one is when you design the house, you do simulations. So you do structural simulation, and the idea is to use as less material as possible, but still guaranteeing a good structural performance. And the other one is the thermal performance. So for instance, the amount to define the thickness of the insulation layer, we did it through the use of simulations from the thermal viewpoint. So, and the other one is that when you put the house on site, you choose the way you design the house and the orientation of the house on the plot depends on the conditions. So for instance, in this case, the big windows are facing south and there are very small windows on the north side. And so the idea is to maximize the capture of sunlight. So again, so we are taking into account site conditions on different levels. In summary, the design of the material, the design of the building solutions, and the design and implementation of the house as well.
Thank you.
Thank you, David.
Any more questions? Okay. Thank you very much, Professor José Pinto. I hope we can see briefly another event.
Yeah.
Well, I think I said what the audience think very well. Very thankful for your presentation. Thank you very much.
So thank you, Franklin and David, for the invitation. It's a pleasure. I just regret I'm not able to be there. So maybe next time. And if you continue inviting me, I have to do more work because, I don't want to show the same thing over and over again. So your invitations make me work hard. So thank you very much.
Thank you. Mm.